moose and you won't get trampled. Like the rules in Michigan for animals are not that complicated to follow. You know, don't try to pet a wolf. You'd be fine with it.
Okay, we're on to part 3 of the S-120 Helicrafters refurb. Basically, we've made the receiver safe. Now it is time to do an alignment on the receiver. And going through the alignment, I had mentioned kind of off the cuff that we had done the recap. You know, the recap is where you take out the old capacitors and you replace them with the new capacitors. And I had ordered a kit from Hayseed Hamfest, and I used most of those capacitors to recap the set. So there was a comment. My friend K1OIK, Bert, he seems to always wink at when I mention that I'm recapping something, that it's a waste of time maybe to replace some of these capacitors, which probably are still good, you know, after 40 or 50 years, 60 years. They're probably still fine. So as a special treat during this video, I'm going to test the actual capacitors that I removed from this receiver. Not this pile I have here, but the actual capacitors that I took out of the receiver to see if I'm just wasting my time. You know, I could be wasting my time replacing these capacitors. This might be the most incorrect thing that I've had on my channel. So let's see if it's true or not that it's good to replace capacitors in some of these old radios. Okay, we're ready to align the receiver. The receiver has been recapped. Basically everything's been checked out. It all functions. We're going to be putting it into the receive mode. The BFO control is going to be totally counterclockwise or in the off position. And there's pretty good instructions on how to align the set. You'll need to download the manual. Basically you can get the manual off the W5RKL site or the BAMA site. And you'll be able to see not only the operating instructions, but you'll see the alignment charts and the alignment procedure. This is the order, and this is an EIA antenna simulation that you put between your 50 ohm signal generator and the receiver. I personally don't think that this dummy antenna is required. I simply use a 50 ohm pad out of my generator and connect directly to the antenna and the ground terminals and align it to a 50 ohm input, which is more appropriate for modern 50 ohm style antennas. They had this fanciful whip antenna that snapped into the back, and supposedly you put this whip antenna on it and you'd be able to pick up shortwave. Well, you know what? A proper antenna like a balanced 72 ohm twin lead or a coaxial feed line into a dipole or long wire antenna is probably more appropriate. In either case, we're going to be using the ground terminal to a good quality ground. And here's the chart, which you can't read, but once you get the manual downloaded, you'll be able to see this clearer. Let's start the alignment. So notice during the alignment I've shoved this piece of metal underneath the receiver. That piece of metal simulates the outer case being on there, and that might influence your settings on your band, or it might not, but it's just a safety measure on my part. I don't want to go in there and have to realign this thing once I get it inside the case just because something was affected by the case itself. So this piece of metal underneath acts as a kind of a fake case, if you want. Now, if you put the case on and try to do the adjustment by sticking your hand in there, that's pretty tricky. Perhaps you could have a small child do that type of alignment. Also, let the receiver warm up, probably for a half hour, and let your generator warm up too, depending on what kind it is, so you can get the alignment done right. I do everything right into the antenna terminals. Even the IF alignment I do right into the antenna terminals. I use a 50 ohm pad, a 6 dB pad, because Today's antennas we're attaching are mostly 50 ohm type antennas. That's what I tune the radio to. The original network they have in the alignment instructions was for people that were using mostly long wire antennas. So I ignore all of that and go right in with 50 ohm coax and align everything with the 50 ohm generator.
So a little bit of superhet theory before we start. Remember, we have an input filter. F1 is our desired frequency. Basically, we have a F1 that is tuned to the channel that we're interested in. F0 is the local oscillator. This is the signal that we beat against F1 to produce the 455 kilohertz IF. And we know there's two conditions that can meet the 455. FO plus F1 and FO minus F1. So the one we want and the image frequency are both presented at this point, and you have to have enough input filtering to reject one or the other. So the input filter has to select whichever of those that you require. Tuning of the receiver is accomplished by tuning the input filter along with the local oscillator. So that's why it shows that they're connected here. They're ganged together so that they track together to always produce the 455 kilohertz IF. So we know that band 1 to band 3 that the system uses conventional high side injection. High side injection has a lot of advantages with the superhet, but they have to break that rule on band 4 because they're afraid that the 12BE6 mixer tube will not be stable on high side injection. So they take the conservative approach and do low side injection on band 4. So a receiver in which F0 equals F1 minus IF is said to be low side injection. But a receiver that where FO is F1 plus the IF is said to operate with high side injection. Let's take a peek. Okay, let's look at the high side injection. Let's say we want to listen to WWV at 5 megahertz. So we have a local oscillator operating at 5.455 megahertz, and we're going to have an image 910 kilohertz higher at 5910. So I think if you tune the receiver up here to 5910 and put in a strong enough signal, you probably would be able to overcome WWV. However, up here on band 4, where we're using the low side injection, here's our desired signal at 11 megahertz, and we have low side injection at 10.545 kilohertz. Our unwanted is going to be around 10.090. So in this case, a strong 30 meter CW signal could overcome our 11 megahertz signal quite easily. The 30 meter signal being the undesired signal, the 11 megahertz shortwave station being the desired signal. So just wanted to show you what all of this looks like, and now we can get on with our alignment. And of course we're going to start with aligning the 455 kilohertz IF. We'll go right into the input of the receiver with a strong enough signal to bleed right through the 12BE6 mixer and give us an output on the IF frequency directly.
So one thing to keep in mind when you are starting this alignment, notice how the variable capacitor for the main tuning has two identical sections. Your normal All-American 5 receiver has one that's smaller than the other, and that means it's high side injection. So the local oscillator is 455 kilohertz above the frequency that you're tuning. But with this capacitor, both being equal, that should raise some questions in your mind. What's going on here? Turns out that Hallicrafters, with all of that knowledge going through the S series, like the S38 and so on, they learned that if you use high side injection for the first 3 bands, that works out good. But once you get to band 4, you need more injection, And that's just the time, or just the place, or just the frequency that the 12BE6 mixer stage is starting to fall off. That means its gain is going down. It doesn't oscillate with as much output power. So they decided on band 4 to go to low side injection. If you don't know that, and it's not really outlined in the manual too well, then you will have a fun time trying to get band 4 set up. So next we're adjusting the IF cans for maximum. I'll set at 455 kilohertz on the counter. Just a little trick to see if you're high side or low side injection. This is band 4, which is the band that we want low side injection. So I've just taken the scope probe and laid it in between the two plates of the fine-tuning capacitor, and I'm running that right into my counter, and you can read 13572 or something like that, and I'm tuned to 14 megahertz. So that's a quick way, and it doesn't disturb the frequency too much. You know, it's enough to tell what's going on, which is important. Okay, here's an old alignment trick. We're setting up band 3, and I'm set to 5 megahertz, let's say. 2 times 5 megahertz is 10 megahertz. Happens to be towards the top of the band. So I adjust my coils down here, but I adjust my capacitors up at 10. I don't need to touch the generator. I just go up to 10. And the second harmonic of the generator will be weaker, but I should be able to at least find it. If not, increase the generator output power. There it is. I haven't had to touch the generator. That's a little bit off. Not bad though. So that's a quick way to set the high and the low coils, capacitors, and not have to adjust the generator.
So please do go to my 2020 video on the S-120, which was the first one that I did up. You might learn something, or I might have something in that you won't see in this video. Here's a series of alignment diagrams that I did that I think you guys are going to find really useful, especially trying to read that ancient manual from Hallicrafters. And at the end, you'll see the BFO alignment, which is a little secret trick to make the BFO work better. Once you've got the caps changed, you play with this top control on the IF can, and you can get some magic and get that BFO to work a little bit better.
So the Hallicrafters S-120 as a Parks on the Air receiver? Well, maybe that's a stretch. How about sideband? Digital?
find a good copy on you, and Ray nearly, Ray, you too. There's normal,
Anyway,
powered cars. You know, that's less taxing on the environment. If we're really truly
Anyway,
worried about
with new
on the
capacitors,
environment and all, I think that would be the way they would want to be going.
the
Not
BFO
taking
is
minerals out of the ground.
quote unquote
And
usable.
what are they going to do? Their electric vehicles are going to be absolutely useless because there's not going to be any more minerals to create the batteries to power them. So,
Anyway, just wanted to let you know what the S-120 can do on sideband. Okay, this is the ZM3-U capacitance analyzer. Now, of course, this thing was calibrated, it says, back in 1963, which is interesting. But it's a bridge. And I have hooked up a 001 microfarad capacitor right from the Hayseed Handfest cache that they sent. And we're on scale 3, and yes, it's just about exactly 0.001 on that scale. Okay, here's a 0.001 orange drop. Let's check that as well. And yes, that also is measuring 0.001. Okay, so that's a couple of good caps. Now, this is a 001 out of the set. This is a Black Beauty. Let's measure that, see if we get a dip. We do get a dip, but it's not very much of a dip. I've connected the capacitor under test. This is one of those Mylar Hayseed Handfests. We're going to go over leakage. And we will set the voltage. This is a 630 volt cap, but we'll set it for something reasonable. That's a 600 volt scale. Let's set it for 300 volts. There's certainly nothing in the set any higher than 300 volts, so that's a good place to test. And we can quickly just put it in the milliamps, and as you can see, there's no leakage reading on the meter. It doesn't actually connect the voltage until you flick the switch. That's a safety on this thing. Now let's put the Black Beauty that came out of the S-120 in. Looks pretty good. Not getting any leakage at 300 volts. Okay, so I've decided to look a little bit closer at leakage. And the way I'm going to do that is by using a microammeter. A microammeter that goes plus or minus 100 microamps. It could just as well be a 0 to 50 or a 0 to 100 or a 0 to 1 milliamp meter. It's just going to give me a little more resolution that I can get on this machine. Also, notice we can do 50 or 60 volts here, full scale, or we can do 600 volts full scale. And in the middle is the 600 volts full scale. Let's start with the 60 and this all the way down, because you don't want to break the meter. Should probably put a couple diodes across the meter just for safety. So we'll start with 60 volts. And already we're seeing some leakage starting. Okay, can you see that we have some leakage started? And I've gone beyond 60 volts already. So we'll stay on the 600 volt scale. 60 didn't show very much. It showed just a little bit of leakage. So let's stay on the 50 scale. And let's start bringing up the voltage. Hope you can see this. Okay, I've got 50 microamps of leakage at 450 volts. 50 microamps of leakage at 450 volts. Now you could not see that on this meter. Next, let's put the Hayseed Handfest capacitor on the same scale. We'll bring this down to 0 again. Now we'll put the same value hayseed hamfest, 0.001. Put that in. Okay, we'll start with the 60 volts like we did before. Bring that up. Nothing. Okay, so now we're at 600 volts. Bring it over. Bring it up. No leakage. Still no leakage. Still no leakage. Maximum. I'm at over 600 volts. And there is no leakage at all on the hayseed hamfest, where we were reading leakage on the Black Beauty. So again, the machine's just not up to this fine a grain of work, but I will tell you, the new capacitors are better than the old capacitors in leakage. So I am getting leakage showing on the 0.047 as well. You know, it's only 20 or 30 microamps at 400 volts, but there is leakage. So let's put the hayseed hamfest 047 on there. Okay. Nothing measurable, and I'm up at 500 volts. Okay, so you get the idea. The new caps are essentially zero leakage. The old caps, even the ones that tested good, have leakage. So between the leakage and how that affects the Q of the circuit that we could see in the bridge, these capacitors were worth replacing. Well, remember, this is a late model S-120, and we know that because it has a silicon diode, and the parts don't look too tarnished. You know, it's not like we got these old paper caps like this waxy thing in there, you know, from the 40s and 50s. It's definitely a 1960s S-120, maybe even the later 60s. So this is a Tiger cap. It's a 0.15 400 volt job. We'll run that up to 400 volts. Measured leakage. Okay, see, this one is showing leakage. And that's in milliamps. So it has about 5 milliamps of leakage at 400 volts. That capacitor would get you in trouble. Okay? So, let's try, here's a Black Beauty. This one's never even been used. It's a brand new Black Beauty. I like that. Black Beauties are famous capacitors for their leakage. That actually improves the audio quality. Okay, it is showing some leakage. It's just off the peg, but we got about a milliamp of leakage in this Black Beauty. Let's try another one. Another Black Beauty. How about this one? Ooh! Whoa, this one's unhappy. Wow, that's 10 or 11 milliamps of leakage through this capacitor. So you get the idea. Not all capacitors are equal in construction, and some of them are just very, very old, and the stuff breaks down. Yeah, about 3 milliamps of leakage on the paper cap. What's this thing? This is a 0.05 400 volt. Okay, we're at 400 volts. Yeah, about 3 milliamps of leakage. So you get the idea. Some capacitors leak, some don't. it turns out that the ones that we had in this receiver did not leak. Either they had been replaced before, or they were new enough or high enough quality that they weren't leaking. Now that doesn't mean they were going to operate perfectly at high frequencies. And one thing we know about these little yellow jobs, they certainly work very well at higher frequencies. So we may be picking up some improvement simply by changing the caps out, having to do with their RF characteristics rather than just pure leakage. But anyway, I wanted to show you this machine. The middle one is the insulation resistance, which I'm not really interested in. That has to do with how the capacitor is built. But that is the simple ZM3-U cap meter. It's a bridge and it's a high pot able to measure leakage. A little bit fuzzy here on 15 meters. Remember, at 15 meters we're using low side injection. But it is working. Digital M15.